So, good afternoon for me. The reality is that sometimes you have overlapping during these lectures, but this high level of speakers has a lot of experience to transfer to you. And before I start, I will try to give some issues very relevant to the questions already said in the previous presentation of Georg. Fantastic presentation. Um, Take into account my experience. I work in this field for more than 30 years. We have some bottlenecks and constraints which are not very visible in the laboratory scale. For instance, the scale up and the infrastructure we have is not so flexible. So the scale up is not that we select the scale, but we have to take into account the available infrastructure, or we can construct some infrastructure, but the rest should follow some specific specifications, take into account the safety or the performance of the material in large scale, but also take into account things important like cost. As concerns the efficiency, everything is depending on the time you have to do this. So you can have high efficiency, but with very cheap, for instance, by using some cheap acids, dilute acids, but it will take too much. It's very long, so practically take into account the needs of industry. You cannot meet them. It's just for experiments in large scale. So you can use very cheap processes, really very cheap processes, but usually this takes a long time. So I will try to put together different technologies as concerns this high value products already discussed and presented, and this is one of the major, let's say, target of agriculture project. But I will try to see more systemic issues and cover also the part of industry, which is more or less something we have long experience during the years in the lab, but also in real scale. Biomass internally has some basic, let's say, exploitation. Traditionally, heating and cooling, these are the traditional uses. Still today, it's solid biomass covers the 70% of the renewable fuel demand in industry and buildings. Still is very high and still is used, although, let's say, something old. Also, it's used during the last years, especially take into account the neutrality in terms of greenhouse gases. It's used for produced biopower, but to be honest, is not the leading. Leading is done by other sources, and also somehow is mixed with waste, but practically my recommendation to you is if you have to select to use biomass or waste, not both. Biomass is material, you know exactly the more or less the content and specifications. Waste is totally different. Usually, the liquid biofuels represent 20% of renewable fuel demand in transport, and also we see some materials as already referred better than me by the industry by York. As concerns the technology, biomass is very, very broad, and while I'm presenting that one, although the project is for algae, I'm trying to go back some steps to show what we know, and also some of you, I'm sure you will find a way to exploit also for macroalgae. And what this means conversion, means to transform something organic into energy or other forms, in this case in energy, like fuel, heat, or electricity by using engineering methods. Yes, these methods can be also integrated in existing fuel distribution infrastructure and can cover part of the demand. And the critical issue about biomass is that it supports the goals, the global goals, SDGs, and also it's useful for security because it's a storage. It's like a battery, so we keep energy as it is, and we use take into account our needs. One critical point is how neutral is the biomass, but okay, let's say theoretically, considering the green cycle of carbon, biomass is neutral in terms of greenhouse gases. I follow. Next one also. Yes. And why convert, let's say, the biomass? First of all, we would like to reduce dependence for fuels or for other, let's say, resources. This is the first issue. But you should take into account that biomass was the first resource we used as a humanity to produce heating or to cook. Before hydrocarbons, there was biomass, and we used for it was the beginning with fire. So it's an old, and if you would like to see a most active role in the current world, the modern world, you have to take into account to understand why we stopped using too much biomass. Was the economy only, or maybe there were other parameters like let's say the comfort to use electricity instead of biomass for some resources. But of course biomass is also important, as already referred in the previous presentation by Georg, as a very important feedstock for industry. Um, Biomass can be exploited locally, but as I referred already, if you go to rural areas, you see to use biomass less and less, because biomass needs handling, needs transport, needs effort, and we, the human beings, prefer more easy ways to do our job. Um, Biomass is also a kernel for circular economy. If you would like to apply or to research circular economy issues, for sure, we have biomass in many different forms available to reuse and to exploit, to reuse to produce other materials or exploit it for energy or other use. So for any real activity on circular economy, you will meet the biomass case. That's why usually when we talk about circular economy, we use also an old terminology called bioeconomy. Bioeconomy, circular economy, and under this, everything can be take into account the resources to be including food, including all these things. And also, of course, biomass is not, I mean, practically, biomass, the exploitation of biomass for energy creates CO2. But as I referred, this CO2 take into account the green circular, let's say, processes of CO2, photosynthesis, again goes back, and we consider that biomass is neutral in the annual plan. It's neutral. The most old technologies used to be thermochemical. Why is important? It's very important because there's a long, long history of these conversion technologies with specific limitations, and we can learn from these previous technologies. Why? Because even thermochemical technology, thermochemical process is not the main target. Maybe the knowledge from the past is useful to combine the biorefinery by using waste of this biorefinery in a very efficient way. Combustion process was the most old one with low, let's say, relatively low efficiency. Gasification is the other one. Syngas, mainly monoxide and hydrogen. It is an old, let's say, an old process an old used in during the previous century for urban heating, but also cooking and with networks. Pyrolysis is more advanced because who can produce with pyrolysis biochar. Biochar is has a very high content and combined with bio oil, the heat value is really very, very high, very close to hydrocarbons. But as already referred in by Christos in LCA, we have to take into account the full chain. So I have done this analysis several times, but in terms of economy, but also in terms of efficiency, I'm not very sure that we can solve. We'll spend a lot of energy to create this bio oil, really a lot high quantities of energy. And another is, let's say, something more simple to increase the fuel properties and confining ability. This torfaction, it is its treatment is used just for complementary, but it's not something very important and widely used in our days. As concerns the biochemical conversion, already referred to fermentation by microorganisms. I have done this. I worked in the laboratory for 3 years trying to convert sugars from lignocellulosics to bioethanol and other chemicals. Interesting process, but we have to do a lot of to improve. The problem here is that the fermentation is done usually in liquid phase. Liquid phase means a lot of water, so at the end we need to separate the water from the product, which is really very, very intensive, very, very energy intensive. The methane is a common process we know from other uses. This could be a very simple process, and maybe anaerobic digestion could be complementary to other processes, not only due to regulations. I mean, regulations for emissions, but also to the availability of residues from other processes. Something which is very important and take care of this. I think maybe you know already, but it's very important for me to refer to this methane, let's say, impact to greenhouse gases. in terms of equivalence. Methane is between 21 and 29, much more active than CO2. Practically means that we prefer to burn to burn methane instead to leave it on air. This is the reason because in all areas where we treat waste, we concentrate this methane. So anaerobic digestion is a simple, let's say, simple process and useful process. Cannot be unique, but can be complementary to other processes. Um, we have several types of biofuel. Bioethanol and biomethane are the most common, but from sugar, from fermentation. But also we can discuss already with biodiesel. But as referred, macroalgae have no too much lipid, but yes, microalgae have. And also, we'll have to see these waste treatment benefits. This is part of our research with Christos Nikoloudakis under iCulture, how to make the full production chain more and more less with minimal carbon offset. Some chemical and physical processes. We refer to thermochemical, we refer to fermentation. Let's go to chemical and physical. A typical example of these chemical physical processes is transformation of oil and fats to biodiesel. Created esters, and this is we say something later. In parallel, we can have some physical pretreatment. Pretreatment covers hundreds of different methods with acid, with size reduction, with alkyd, with drying, mechanical, any kind of idea. Different processes, and you can find some list of these processes in if you Google our work, but the result we're not very happy. We have to do a lot of work in this exploitation of biomass for low value products. That is the reason, because we need biorefinery and we need high value products to combine all of them together. And also something which is really very, very important for the future is material production. Why this is important? Because we need for several uses materials to minimize the environmental impact. For instance, materials for construction, materials for protection, materials for different uses, materials for even for insulation of houses. So biomass and the careful processes can give us some new ideas, not only on bioplastic, but also materials with specific qualities. We have another project, how to protect heritage, protect let's say heritage buildings, or heritage, what is heritage or culture. And I think we see a new trend to use these materials not for energy, not for high value, but to create materials with some specific characteristics. Usually we have a lot of applications, as we referred, electricity or for transport, chemical materials, and of course, all these uses of biomass support decarbonization and energy efficiency. Um, I will continue with some specific elements. Um, so, advantages. Biomass conversion creates energy and materials and can help rural development directly. If if today is not operating, is becoming weaker and weaker, we have to understand better why. And comfort is one, as I already referred. The other is that uh, this collection issue from costs also. We need people, and we have to pay people how to do. Maybe in the future, more autonomous collection system of biomass can make everything more cheap and more useful. Some challenges. First of all, and please is number one challenge for biomass, availability. Number one is availability. You cannot build a process, an industry without taking into account this availability, because this is another also bottleneck for the scale. eh? So we need to make profitable what we do. We need to be sure that we make safe the supply of material. This is number one. Something also which is not referred here is the quality, the content. We need more or less somehow we need constant for industry supply, or not the same, but very close, which has really big impact to the final product. This is the bio materials have the previous history, and several times we see the history of these materials during the processes in the final stage. We see so whatever can be done better in the beginning can have a good impact till the end. Bad solutions in the beginning, maybe they will kill the product. I will give you the result example later. And policy referred already. One weak point in Europe is that although there are there's a policy framework for materials produced inside Europe, and this is really very strict. And of course, this is good. This frame cannot be in a safe way applied with importing materials outside Europe. So Europe have some rules how to produce in a sustainable way and the quality, blah, blah, blah. What we can do is when we import to check the quality of the import material, but we don't know the real history. And this is an issue, very sensitive issue in the biomass industry. I will focus because I have experience to biofuels, because we have long experience with biofuels, only as example for you to maybe to get some ideas for other exploitation of biomaterials like microalgae. This is from International Energy Agency. You see that the projections are here. We see that after 2020, let's say the global emissions somehow were ready to be less annually, but you can see this purple color. The aviation is a problem. So talking about biofuels or other materials or fuels, uh, a key for research to improve and opportunity, and people, you know, have very good chances if you work in submission of fuels for air to be successful, because there are some teams, but not too many teams who can do this work very well. So number one problem is the aviation. And as concerns the rest, you see they are minimized and close will be somehow maybe to end. Okay, this is one point to take into account. Opportunity for air use. As concerns the biofuels, there are different uses in Europe. This map, the maybe uses most take into account, the consumption is depending on how big is the country. But if you see from this map, France and Germany are the main consumers. There are several bio industries for biofuels. In Greece, we have mainly biorefineries used, which use not only first generation, but also they use residues from other sources, and who used cooking oil. I will show you later an example. Sorry. Okay. For EcoSense biofuels in this case, we have four generation biofuels. First was from food crops, take the sugar cane, and somehow you can process the sugars and ferment and with other uses. And the same with soya beans or other products. But this was not sustainable. I mean, we're missing food globally. We miss food in Europe. China is missing food, so I don't think this is reasonable to cover and to produce instead of food to produce just the material for biofuels. The second generation was for crops. Again, with crops from and crops from agricultural waste. Mainly, the structure here was lignocellulosics. My long experience was on this second generation biofuels. The issue is how to process lignocellulosic materials, how to destroy the the structure with different ways, pre-treatment, whatever it is, and produce sugars, enough sugars for further processes. The problem here is that in parallel to the production, you have also the degradation of sugar to other products. The third generation biofuels, we have done some work also here, is from microalgae, usually, and also other microorganisms working, let's say, developed and cultured in wastewater. This solution is interesting in terms of research, but I will show some indicators. It is high energy demand. I don't think that is exactly sustainable, but could be under conditions solution. And the fourth generation, somehow we try partially this issue in under our work in agriculture as a team, working also with microorganisms, but we're not very ready to make an announcement. We hope till the end of the project we have some results how to modify the microorganisms and make them more productive. This is really something for the future and very important. As concerns the bioethanol from lignocellulosic, we have something like hydrolysis to separate hemicellulose from the rest material, but not only hydrolysis, we have also other pretreatment ways. For instance, to put everything on water in order to break the lignocellulosic chains, or maybe somehow to use alkali and to help this deconstruction. But it's interesting, but if you're interested, we can discuss. You can send me an email about that because I have spent several years of my life on this. Hydrolysis is the main way how to break the crystalline glucose and produce exhaust. The majority can be glucose, but it's not only glucose. Why glucose? Because exhaust D-glucose is very popular for microorganisms like Cerevisiae saccharomyces. And at the end, the fermentation is the last part to convert sugar to fuel ethanol. What's the point here? If the sugar solution is very diluted, the productivity of fuel ethanol will be not very high. Meaning that if we would like to get fuel ethanol or other problems or other products, we need to separate it from water. And guess, if you have for instance, an ethanol car, or your system cannot afford more than 2-3% of water. Practically, we need to find smart ways and less energy intensive how to separate. And we have these solutions, but we can guess why bioethanol is not very popular. It could be a solution, but not, let's say, very popular. So we prefer to see other products by fermentation, which have higher value. Hydrolysis can be enzymatic or with dilute acid or with concentrated acid. This is the game. Enzymatic means that we use some enzymes. Enzymes are produced from microorganisms to help this degradation of the material. Enzymatic means high specificity. That means it's very special how they react, how in this Lego construction the enzymes come and meet the structure of ions or other chemical elements and help to create the bridge to create the synthesis at the end. But it's expensive, it's very specified, and somehow lower. Dilute acid was most classic because you can use some acid, classical sulfuric acid. We avoid others like phosphoric or taken with nitrogen or whatever it is. So this is most common, but we're not very, we don't need too much to be very clear. And it's to help just to break this change. And also concentrate is very powerful, but in addition to the safe regulations for equipment and environmental, concentrated acid is concentrated. So you need to act very, very, very quickly, and maybe you destroy everything. In a refinery, you have also all these stages in, let's say, in implementation. This is also, this is the photo is in laboratory level, lignocellulosics, and we can, let's say, separate the lignin, which is the black liquor, and the pendose and all these things, and try to ferment the exogenous part. Okay, this is a simplistic way to present these processes. And this is the key. Cellulose to glucose, let's say big part glucose, not only glucose, but big part of glucose, and then degradation products. Why I'm presenting that one? Because cellulose is something something sensitive, and then when we produce glucose, under the same conditions has a trend to go to degradation. So if we leave a lot of this process for a long time, everything will be degradation products. So we have to act very fast, if possible, to produce glucose and to avoid degradation products. Why? I will explain later. This is not only because we high the efficiency, we lose the concentration of glucose of raw material. We need glucose to ferment, but also we do something very bad to this liquor. The K is the Arrhenius equation, but if you see in this Arrhenius equation, which is typical, take into account energy for activation, R and T, the temperature, has this coefficient Cn. C is, we have created some models and have published as concerns the role of acid in the kinetics of cellulose transformation to glucose. This is the catalyst of acid, the acid catalyst playing this game. And here is the very important issue. Deglucose, sorry, producing furfural, and diglucose is producing hydrometylfurfural. Two elements, which is important. Both of them are poisonous, can kill the material, so they can stop the operation of the microorganism. You cannot ferment, or you can make it much slower. So these degradation products have double effect. One, they minimize the concentration in glucose. The other one, that they create inhibition effect. Inhibit the fermentation of the product. In this table, you can see some of our models we have created in the lab. This is relatively old, it was before 15, 16 years published, but we have created some kinetics of lignocellulosic hydrolysis for different materials, corn stover, wheat straw, hardwood, etc., etc. You know, this story continues, and it remains fresh, but in our times we have more tools to work. I see some messages in the chat. Apologize, I have only one screen. I will keep some time to discuss at the end. Important algae, macroalgae, as referred already by Georg, no lipids, but microalgae, we have a lot of them. So this is have a lot. So we can produce somehow, and to see a full chain and this life cycle, And this can be an opportunity for the future, yes. But we need big surfaces. You can see this picture. Um, and also have to combine. It will be open or closed. Open means that it use the natural light for photosynthesis. Closed means that we need something like artificial conditions, which is very intensive in energy. So potentially you have large surfaces with water. Yes, we can develop some cultures and to see, but always the land is an issue. Most of the wars were done for land and for energy. So, uh, but it's not something we have to forget. As a humanity, we have a lot of experience from previous researchers, and now, with all these tools we have available, we can select and we can exploit the previous knowledge for other applications and create innovation. And the best for closed system in our analysis, in the case you have examined, 90% of the environmental problems were due to energy. And also something very important is that by using the co-product from algae exploitation, minimize 50% the total environmental footprint. Look at this. This is pictures from a paper, of our paper, published before 5 years. We compare different microalgae cultures, and you see that in both cases, the open system is we have two types of spirulina. One is spirulina platensis, the other is nanochloropsis, and the impact is the rand is to human health, green ecosystems, and the yellow one to resources. And you see that in open systems are much more efficient with less impact. Um, so this is very important finding. This is the reason because the journal this is a good journal and publish it. And look at this also, which is and sorry, another analysis done before 6 years also, using industrial data from comparing biodiesel from used cooking oil, first generation biodiesel from sunflower, petrodiesel, and microalgae. And yes, microalgae in our analysis had higher impact than petrodiesel, which was really a very important. This is a finding. This is a popular analysis. So, give you. I know that maybe you see what this is about. No, try to think the same way, compare with LCA with other methods to see this impact, and you will be surprised when we take into account the full chain of your findings. And this was really a finding that microalgae to produce biodiesel from microalgae was more environmental problem. It was a bigger problem for the environment than petrodiesel. And something about this transterification with lipids, the use of free lipids with methanol and the catalyst produces glycerol, and famous materials there is biodiesel. Okay, that's for you. We have checked the production of this biodiesel products by following EN 14 2000 to 213, and we have seen that this biodiesel had a very good, let's say, very good characteristics following the standard. And in Greece, usually this biodiesel is mixed with diesel to cover the highest part. Now we try to be more than 7%, but always we're missing the raw material to change the lipids, and we're missing material. And the other is this table is from another other publication we have, and could compare this behavior, and according to EN 14 2000 to 214, and we compare this biodiesel from used cooking oil collected from different countries, from Greece, Spain, and Portugal. And we have seen that the quality was also very close to the, let's say, to the diesel. And some technical challenges is the contamination from food when you use the residues, the used cooking oils, whatever it is. So it's the history behind this residue. The water is always a problem when we like to burn. So, but it's the same. For instance, we would like to separate for high value products. We need to dry. This drying process is really very heavily in terms of energy. And also the stability of all these products is not very high. So bioproducts are very good, but the stability is smaller than the let's say these products which are linked with petrol, but this is, I think, the main advantage. So it's not forever. So they have some time, but we need to know how long this system can be used. For instance, we know that for biodiesel, we need to consume during the next year. It's better after the first year. The efficiency is coming less and less. The same with about biodiesel. There is a lot of studies on this, but okay, this is not. And we before some years we got a prize to create a system which was very autonomous with my students and with students from Cameroon, and I was happy with this because it was mainly a global competition at the UNESCO, and my students took this. You cannot see me in this photo because my students were the winners. Um, Something important, of course, is not the same like again like macro algae, but could be a very good example for to use for this some purposes because we in as maybe you know that in Mediterranean we produce a lot of oil. This is famous, well known, and but we produce a lot of used cooking oil residues from houses. So practically, if we cannot collect this, it goes to waste treatment. Means energy consumption, materials consumption, pollution. And what if we can select that one and reuse? So the idea behind goes to create a full chain, how to collect from houses, from restaurants, whatever it is. In the most of the cases, restaurants were more organized and start from material and to produce at the end biodiesel. This system is still in operation, and we can produce about 70 liters of biodiesel per day with this system using from, and we have created some campaigns for this. in cooperation with each municipality, with the people, with if you can see how construct with a cheap, very way we use very cheap material now during the years, and we hope that very soon we'll be happy to show you the next generation of collection points. And you can see also our team, they put sensors inside to monitor what's going on. It was a competition with children, so every every year the children in the schools collect for several years they have done this collect the used coal for the houses, and at the end the schools get something good for them, let's say for a laptop or something like that. This is a very important point. Why it's important? Because you can see in these pins, this 30, uh, uh, 30 places you have put the collection points in around an area in Crete, and you can see also the monitoring of how complete, how full is the collection point. Very important because this material took a very high price. Um, if you have concentrated this material, you can sell almost half euro per liter. You can sell used cooking oil about half euro per liter, which is very high. So you need to control all the collection also for environmental reasons. But we used this experiment, let's say, was not very expensive, our construction. So this system was operated for 3 years and were successful for the results. And I will try to conclude some things I hope will be useful for you. Um, First of all, the conversion is mature. That means that in most of the cases we know a lot about the technology. In some cases, for instance, the thermochemical, we know too many, maybe more than needed. And what we do is we try to connect the impact of one process to the other, the chain. This is somehow the new thing. So the impact and to monitor this impact, and to also to exploit all the possibilities of biorefinery, exploiting experience from, for instance, we can use some experience from thermochemical to exploit in thermochemical way residues from macroalgae. Or in the case that space you have something which contains some lipids, you can exploit. It's not very common, but you can have to see how there's no need to start from zero. This is what I need. Have experience, and I see around me a lot of people trying to start from zero, but zero is not the solution. We need to go further. We have a lot of information, we have a lot of experiments. What we need is to combine, for me, all these elements together towards the scale up. Critical values is the composition. We need to know the content. If the content is not proper, that means that all the next steps are risky. Everything will become difficult and more difficult to achieve good quality product. The second one is about the conditions of reactions. Okay, for us who are chemical engineers or environmental engineers, we can control somehow what is there, but okay, we cannot live forever. It's like the food. We cannot cook and leave the food for days cooking. So at the end, everything will be degraded, either under soft conditions. Energy balance, energy balance. I have met a lot of people who make optimization in one area, in one process. For instance, optimization of fermentation, optimization of breaking cellulose. But if you connect all of this, the result is not very good. It's not very promising. So energy balance and emissions is something which follows us in every stage. Not because we are good people or let's say we love too much the nature or nature-based solutions. No, because energy is there. If we transfer something from away, we spend a lot of energy. If something, so the solution could be to find what is close and to exploit what is very close. The water use is another issue because it's not energy, but when we spend a lot of water, this is another problem. We are missing water. Year by year, the water quality is becoming less, and also the population of world is becoming more. So there's a high pressure on water. So we need to somehow optimize the water use. LCA is the standard tool. If you learn, it's after that you can make your assumptions with functional unit or the chain. It's presented by Christos Nikolodakis. But we can play, and we see very, let's say, very strange things in this frame. Frame is number one. You can create a frame where everything will go fine, and if you grow this frame, maybe the system will be negative. Techno-economic analysis is also a bridge to deployment, but techno-economic analysis, when you have a low level of maturity, of low TRL, what means cost? What means cost for something very, very new? Of course, the prototype is very, very expensive. And for sure, we would like to be grateful to those people who make this experiment before us, the engineers, in order then to exploit this knowledge and to make it real products for every people. So techno-economic analysis for brand new findings, I cannot understand what's the meaning. It's not profitable. This is the reason, because we need money, co-financing from several sources like the European Commission, national sources, or other sources. The laboratory results going to the pilot cannot translate. This is the reason because why we go back stage by stage. We have already referred to this, and Georg referred to this. And also what is about the policy, the market content. If tomorrow the policy content is to use only biomaterials, the full market will change. This is clear. So the reality is depending on our decision also. Some publications, all this presentation will be uploaded in YouTube, and you can see a list of Google these publications. I try to give you some a broad, let's say, a broad definition, description of our experience till now, hoping that we offer some good ideas for our future. And something very good, usually the infrastructure, the laboratory we used as a lab for these experiments were not very, very expensive. This means that You can make fantastic analysis, fantastic work with no high cost. But please exploit what happened before you as there are generations who work on this. Thank you for your, I hope it was not very boring, Christos, and I will try to see if there's a question.
Thank you. Thank you very much,
No
Professor.
question.
Yeah.
Ah,
There
Yuko,
are,
yes.
yeah, thank you.
Yes, something, yes, I'm
There
confused.
are two, yeah,
Yes.
there are two
Some,
questions
yes, please.
in the chat. Yeah. Uh, One is about what is the real solution to apply laboratory results to the pilot scale in biorefinery?
This is, yes, I think we have already referred to this also, Georg. What we do, also Christos, that's the same thing in LCA. We try to translate laboratory results to real scale. What we do is stage by stage. There's no other solution. We start from TRL 1 to 3, then we'll go to 5. From 6 to 8, we're more closer to the reality, and 9 is something commercial. Um, and it's different, totally different behavior from glasses to the real, let's say, real reactor. I told you it's not only the scale of the reactor, but also the behavior of the material is totally different. It's very easy for you, for instance, to heat a small quantity of water in seconds, or but what about have a large scale reactor, for instance, some meters, cubic meters big? You cannot heat at once. You need some time to. The same with pumping system. You need, and you have to take care that it's like a Lego. You can build very easily, let's say, a reactor, but you cannot build the exactly size of the pump you need. You cannot. So, or the piping, or things. So, what we do usually, the industry, they try like a Lego to combine different parts of the process and to create the new industry. Otherwise, very expensive to produce just for you something. It's out of the cost. And the other is about Yuko, correct? Am I correct, Christos?
We have actually, it was about, yes, what is the definition, but it's used cooking oil.
Or
There
some
are,
people, sorry, just to add,
there are,
you can find this waste
mm,
cooking oil also in the literature. It's the same.
mhm.
Very important for countries like the Mediterranean countries. Very important this issue.
There are two more questions.
Yes, please.
Yeah. So we need the raw materials to apply these technologies and obtain the products that we want. The skyrocketing demand for macroalgae supply is not being met by supplies obtained from the seaweed farms and from the wild harvest. How do the macroalgae biorefineries respond with the challenges and demand of the algal supply to keep the production going and still sustainable?
This is not one. There is no answer, I think. The answer is parametric. I mean, macroalgae is something. When we discuss macroalgae with some friends, we have some colleagues working in in the inside the sea. Some by biologists of the sea, marine biologists, they're afraid. Say, well, what we do? Maybe we do something very bad. I mean, but we needed first of all to be more pragmatic and understand better what is produced, as already referred by Georg. We have some areas where it's fast growing, so we can use very easily, I think. But I suppose that in some other areas we have to keep it as it is. For instance, it's not microalgae, but something similar we have in Mediterranean, the Posidonia fields. So we have to be very careful about the quantities. People who have done the same mistake with fishes, especially in there was overexploitation and a risk at the end. But if you are wise, or you are wise, if you are a fisherman, you need to take into account the sustainability. This will be, I think, the main way for this exploitation. Sustainability. Sustainability means to produce something, but to be ready to produce next year and say in a very safe way. And safety of supply, I referred to the beginning of this presentation, is number one for industry. Without material, without raw material, we have no industry, nothing. So we need to follow sustainable methods for and in that way you need to protect also the production of the macroalgae. I hope if my answer was not enough, please send a message and I will be back again.
And
the future of
there's
macroalgae. Yes.
yes.
The future of macroalgae refineries refer this to produce several products. That's why I selected to show you the fuel, which not high value, but have large qualities. So we need to see how in the biorefinery we can learn, for instance, consider the petrol material introduced to distillery, and the issue is from refinery to distillery. Sometimes in my mind, I'm confusing that. I mean, distillery has taken into account the different specific weight, taking into account the temperature of the materials. So you can separate, and at the end, you need to use everything. So the answer is optimization of everything. Is exactly compatible with the circular economy, let's say, philosophy approach. Nothing is let's say, can be energy sufficient or energy neutral. But we need to exploit everything in that way, minimize the use of materials, and also all project becomes very economic attractive. For this reason, we need to take into account some rules like industrial symbiosis, meaning that what is here can give the feed for the other. Maybe the valorization of the residues can give answer to energy production, or also biogas production can give us not only better environmental performance of the waste, but also resource for energy. Yes.
Great. So I don't see any other question in the chat. Thank you.
I would like to thank all of you. Thank you, Christos, also, because Christos remains with you very late just to support the project. Please keep in touch. We have a lot of ideas, if you wish. And as a lab, we have experience not only from Europe, but also from other areas. I don't know if someone from Australia, New Zealand, or there's one from Philippines, I think. Yes. Okay. Thank you very much, and keep in touch.
Thank you very much.
Please stay with us for the next two presentations on Monday. Yes. Thank you.
Yeah, thank you very much. And we conclude the day 3 today, and we'll see you on day 4 on Monday.